So remember this, that we just proved that if we have a linear transformation and we have a linearly dependent subset of this domain set, then its direct image is linearly dependent. And our approach was this, that if I have linearly dependent subset of Rn, then what happens is this. So I meant actually, therefore, we should be able to find these scalars, okay, able to, sorry about that, be able to find these scalars, alphas, which are not all zeros, such that what happens, that this linear combination of these vectors v1, v2, v3, v4 with the scalars alpha 1, alpha 2, alpha 3, alpha 4s will be 0. Now we have to talk about the direct image. So what did we do? We just applied this linear transformation T on the two sides. And what are we going to get from out of this? This we know under linear transformation, this is 0. And for this, what we had got, so because T is a linear transformation, okay, this quantity would be what? This quantity would be the linear combination of the images of the vectors, and the image of 0 is 0. So what we have is that we have been able to find these not all zeros, such that this linear combination is 0, and therefore this, as we wanted to say, this is a linearly dependent subset of Rm. Last time we did that in a little exploratory manner, but this time we are just writing directly the way, or a way in which this is proven. Now let's check this question, that say we have a linear transformation, okay, say the same one or different one, and we have a linearly independent subset of Rn. They don't have to be 4 vectors. I just took 4 vectors as before, but we it will apply on any number of vectors. Now, since we are looking at linearly independent here, remember this, that our n has to be greater than or equal to 4 if we have 4 linearly independent vectors in Rn. So then what we would like to examine is this, that whether the direct image of these vectors is a linearly independent subset of Rm or not. So what the criteria for that will be? Linearly independent means not linearly dependent. So what we have to check is to check if we have this, that if we got a linear combination, let's take a different coefficients here than the discussion before. So if we have a linear combination of these 4 vectors, okay, then which is equal to 0, then the only way this can happen is that all the scalar coefficients are 0, right? That's what we have to see. So let's check that here. Okay, so this is 0, and whether this implies that all these all these scalars are 0 in values. That is, yeah, I'm sorry, I'll be writing this in a little weird way, but anyway, just have a little patience for me. Okay, so that is whether this happens to be true or it is not. Okay, so Now, if we look at, first of all, I said 0, but I forgot to write it. This, because t is a linear transformation, what will this translate to? So, it will translate to, or, t being a linear transformation will mean that this linear combination is the image of this linear combination, right? Now the problem is this, that if this equation is, if this quantity is 0, we can't conclude that this will be 0 as well. I mean, that is, it's not necessary that anything landing to 0 will be 0, unless, if you recall, T is a 1-1 linear transformation. So here, unfortunately, we are not able to apply that argument. And a reason is similar. A reason is simple, as we just said, that it's not necessary that if the image is 0, the pre-image is also 0, or only 0 is landing at 0. And there we can construct our example that here, if we take, or a counter example, that if we take this such that what? Such that tu equals 0 for all u's, okay? All right. So we may say for all u, all right? Then, so actually all u in Rn, we should say, for the sake of precision, okay? So then T is a linear transformation, all right? T is a linear transformation, and any linear combination of these vectors will be 0, because now they are all 0 vectors, okay? All right, or this actually does equal simply, this set simply equals what? Just a single set containing of only the what? The 0 vector, right? Okay, so here, so this is only the 0 vector, and a set containing 0 vector is a linearly dependent set, right? So what happens here? That in this case, the answer here is what? Not necessarily, or this statement is not true in general, and we showed that by using a counter example.